So chemical reaction mechanisms consist of usually unimolecular or bimolecular steps. To see something where three molecules actually collide simultaneously is extremely rare. So if you think about, if you ever hear a news report of a multi-car collision, it's not actually all three or four hitting at the same time. It's like a chain reaction. You have a collision between two, something happens, and then another one hits, and another and another. So usually it's a series of steps involving one or two cars. So we've already discussed the unimolecular, and now the other important is a bimolecular, where it does matter what the second thing hitting it is, because the parts are going to be interchanged through the breaking and remaking of chemical bonds. So the chemical reaction I'm going to use is a very famous organic reaction type called nucleophilic substitution second order. SN2. Oop. All right. Dope, 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 dope. Let's try that again. The example I'm going to use is a very famous type of organic molecule, reaction type called SN2. So substitution, nucleophilic, you don't need to know what that means, but the two means it involves two molecules. Okay, so we're going to take a molecule, and this is going to have 4 bonds to it, and a three of which, in this example. All right, so let's see what we're going to have as the reactant. It's going to be bromine. All right, so what's going to happen is that we have this bromomethane here. It's tetrahedral sp3 hybridized carbon. We're going to replace the bromine with an iodine. Okay, and so that is the energy here for the reactants. And so when you see one of these energy diagrams, the first minimum is going to correspond to the two reactants. The products are going to be related to the second minimum. But I'm going to draw, first of all, just the product. Okay, so the iodide anion comes in and it forms a bond with the carbon. These hydrogens have to move out of the way. They move to the other side of the molecule, and the bromine gets knocked out. Okay, so this is one step, and so I'm going to more or less draw one arrow, but I'm actually going to draw what the transition state, which is the geometry of the atoms, how they're arranged at the highest energy point. Okay, and so if we look at the very midpoint, we see a partially made bond to the iodine and a partially broken bond to the bromine, and the whole thing have a -1 charge. Okay, so when you take two reactants, you collide them with collision energy. If there's enough energy to get to this point, then it will continue on to the products. If there's not enough energy, you won't get to this particular typical geometry, and you'll just go back down. So what happens is the more and more energy in the collision, the more and more likely you are to have enough energy to get over the height. Again, the activation energy for the forward process is a lot higher than it is for the reverse process, which is, of course, going backwards. Okay, and so Again, we're going to write the rate law expression. So we're going to write the forward rate is equal to forward rate constant times iodide to the first power, because the number of collisions depends on how many iodides we have. If we double the amount of iodides, we're going to double the amount of iodide collisions with bromomethane, and again, the dependence on the bromomethane is also first order. So this is frequently what you get for bimolecular reactions. You get rate constant times the two reactant concentrations. The reverse reaction is a different rate constant, because in this example, actually the height is a lot lower, so the reaction is a whole lot easier to occur. And so in this case, we'd expect the reverse constant to be a lot larger than the forward constant. The forward constant is very, very small because of very few molecules actually get over the barrier. All right, so now the reverse reaction depends on the number of bromides that collide with methyl iodide. Okay, so again, what you need to learn how to do is read a reverse reaction. Think of this not as reactants and products, but actually these two molecules, they're in the mixture, these two molecules in the mixture, and when these two collide, you'll get these two, if there's enough energy. And when these two collide, if there's enough energy, you'll get them converted to these two. And this is continuously happening all the time. And of course, at the thermal equilibrium, where the rates are equal, then we'll have a certain composition, so many of each type of molecule. Okay, so that is an example of a bimolecular reaction step. Okay, so you should be able to write, given a reaction, say, if it's a molecular step, what is the rate law expression? It should be real easy to calculate. All righty. The other thing I want to mention in leaving is that actually the reverse reaction, the products are more stable than the reactants. And in organic chemistry, you learn to prioritize the halide ions in their preference to stay in the molecule versus leaving when you compare one to the other. So it turns out that iodide would much rather be out of the molecule compared to bromide. So iodide is called a better leaving group because it leaves a whole lot easier than bromide does.